number 7 here. So quick stop. Car decelerating at 7 meters per second squared. What's the angular acceleration of those 0.28 meter radius tires, assuming they don't slip? So we know that from prior work, tangential acceleration, which is what we've been given, 7 meters per second squared, equals angular acceleration times r, which means our angular acceleration is just going to be that tangential 1 over r. So a minus 7 meters per second squared over this 0.28 meter radius. Easy peasy, a minus 25 rads per second squared. Part B. How many revolutions do the tires make before coming to rest, given initial angular velocity is 95 rads per second? Okay, once again, we have a delta theta that we want, which can be understood in terms of what we have using the zeroth law theorem expanded in this fashion. 2ds equals the difference of speed squared. So 0 is the final speed because it comes to a stop, minus 95 squared. It's all the right units, so I'm just going to skip writing them. So I know I'm going to get some number of radians out of this. Okay, I'm going to get 181 radians. Well, it wants revs, so if I divide by 2 pi radians per rev, then I'll get roughly 29 revs. It's 28.7, but close enough. So this is just rotational kinematics, really. We throw in a little bit of rotational dynamics, like with the friction thing and torque a minute ago. So part C wants to know, how long does the car take to stop? Well, delta omega equals alpha delta t, which means delta t will be our change in speed over the acceleration. And we already know these things. So it's a negative 95 change and a negative 25 for the acceleration, all in the right units. So I am guaranteed to get seconds, 3.8 seconds for that one. Part D. What distance does the car travel in this time? So I need to relate a linear distance to the things that I know, which are, I know the angular displacement and I know the radius associated with that angular displacement. So basically, x equals r theta. This is our arc length formula. This time our arc length is, in one sense, being laid out linearly. Okay? So the x distance that it goes will be equal to the circumference or the arc length from start to finish, which is going to be more than the circumference of the tire. Okay? Unless this is a really big tire. Right? So x equals r theta. So r is 0.28 meters. Theta was 181 radians. And this gets me to 50.7 meters, or 51 yards, 150 feet, give or take. All right? Half a football field. That makes sense at a speed like this. And then finally, part E. Do the values obtained seem reasonable? And I'll say yes, because if you convert 26.6 meters per second, which where did we have that? Oh, I didn't do the other part of D. So let me back up here. Um, E is what's the car's initial speed? I'm sorry. I'm doing the last part instead of the first. Initial speed, V naught. Well, it's R omega, or R omega naught. So this is just our formula we've seen a couple times. So initial speed will be that 0.28 meters times that angular speed of 95 rads per second. That's where we get this 26.6 meters per second. And so the answer for F is, does this seem reasonable? The reason being is, for one, 26.6 meters per second is essentially equal to 59.5 miles an hour. So this car is going 60 miles an hour, and it takes 50.7 meters to stop it, which is essentially 166 feet. So to put it in terms that we're most familiar with. So yeah, this makes sense. It's believable. It takes about that much time at a normal deceleration to bring a 60 mile an hour car to a complete stop. So number 8. This problem deals with additional aspects. There's a textbook example about this, and so I'm going to be borrowing some numbers that are given away in that example. So some givens, all right, in this problem are, one, that alpha is 4.44 rads per second squared, and the rotational inertia of the object that we're dealing with is 84.38 kilogram meter squared. That's the strange unit for that. So we start with those givens. So part A, how long does it take the father to give the merry-go-round and child an angular velocity of 1.5 radians per second? So I know that I have a change in angular speed that's necessarily equal to angular acceleration times time. Second zeroth law for angular motion. That means delta t is just going to be my delta w over alpha, and my delta w, 1.5 minus 0 over the alpha. That's a given. And you get a third of a second, roughly, out of that. That's part A. Part B. How many revolutions must it go through to generate this speed? So again, we're going to use the second zeroth law in angular form, which can be written this way. Done this a few times now. So I have that 1.5 final angular speed minus nothing squared over 2 times the given angular acceleration. So I get 0.253 radians, but I do believe it asked for this in revolutions. So we have to convert it to revs. So once again, the 2 pi rad per rev conversion, and I get not much of a revolution, which is unsurprising. So 0.0403 revs. So 4/100ths of a revolution, right? A very exciting calculation. Part C. If he exerts a slowing force of 300 newtons at a radius of 1.35 meters, force at a length, you know you're dealing with torque. Absolutely dealing with torque. Force at length means torque. Repeat after me. Force at length means torque. All right, if you know that, then you know what to do when you have force at some length. Right? Which is why we labored all that other stuff. So right out of the bat, I'm like, all right, torque equals I alpha. I know that's coming. I could also write R times force and this applied force here. So what does this get me to? It gets me to alpha is going to be radius force over rotational inertia. Well, I'm given rotational inertia. All right, we knew the mass of the object and what its shape was, we could go compute this, but it's just given away. So our alpha would be, let's see here. Problem is, I need a little bit more uh, to go on here because I know alpha, all right? But I need to incorporate this because the question is asking for how long it takes, all right? So let's uh, step back a bit, and if I were to take the equation that I've already used, delta omega equals that. This equation, delta t, has in it the thing that I just solved for, an alpha. And so if I take this stuff here and replace it there, then I will get my delta W over RFI. So now delta T will be, basically I go final speed minus initial, so this is going to be a negative 1.5 rads per second for that delta W. The rotational inertia was the 84.38 kilogram meter squared. And then radius was at 1.35 meters. And this force, this stopping force, it didn't say negative in the problem, but it said it was a stopping force of 300 newtons. It means it's a negative 300 newtons. And so our delta T, you compute it all out, and you get about a third of a second. So again, this is a kinematics and dynamics problem. We do a bunch of kinematics to get some of our variable values. Then it's a torque problem, all right? And then torque is related to these kinematic variables. Therefore, I can work my way through to find out certain things. So just to kind of review quickly, right here in part C, we immediately knew that we were dealing with torque, which said, okay, I can think of torque in the I alpha form, which is good given that I know I alpha. I was given the acceleration and given the rotational inertia. This is a good thing to know. I could actually compute the torque value, but the torque value doesn't help me answer part C. Part C wants to know how long it takes. So I could say, all right, what if I bring in this other part, which is also stuff that I know, all right? But none of that gets me to delta T. So I need to say, all right, I know alpha. So since I know alpha, it's in this equation, maybe I can use this. Oh, look here, I also know those things. So now I know that I need to combine my torque something or other with my second zeroth law for rotational motion, something or other, in order to extract time out of it. So it's a little bit of an equation hunt. So we had to drill in about 3 layers to get to the thing we needed through a set of other things. So that none of this is hard, but it is tedious. And it's not obvious. It's not like the flow chart for every problem is given right next to the problem. You have to take the available things. What can I get with what I know? Move on to the next thing. All right. One of those takes some this bit. Number 9. Calculate the moment of inertia of a skater given the following information. So part A, I'm told that the mass of the skater is 60 kilograms. Yep. It is approximated as a cylinder whose radius is 0.11 meters. So obviously people aren't cylinders, but you know, the main part of your body, especially if your arms are down, you're essentially a cylinder. All right? An oblongy cylinder, if you will. So the rotational inertia of a cylinder is 1/2 mr squared. We could look this up in a table. We'll do that at some other time. You'll just have to take my word for it. And so 1/2 of the 60 kilograms and the 0.11 meters or 11 centimeters squared. And we get the rotational inertia of the cylinder skater is going to be 0.363 kilogram meter squared. Okay, exciting. Part B. The skater with arms extended is approximately a cylinder of 52 kilograms from the trunk with that 11 centimeter radius, and then 2 almost meter long arms that are 3.75 kilograms each. So the weight is getting distributed. You've seen this to skaters. When their arms are out, they spin slow. When their arms are in, they spin really fast. And that's because you change the angular momentum, because you change the distribution of the mass, which changes the momentum of it. So all we're doing is sort of doing half of conserving angular momentum with a speed skater when they pull their arms in versus throw their arms out. All right. So that means if I do the rotational inertia of the body cylinder part, we already know that that's mr squared over 2. All right. And so with the arms outstretched, if the trunk of the body minus the arms is a different mass, then this is going to be 52.5 times that same radius squared over 2. And so the trunk of the body will have a 0.318 kilogram meter squared. This is good. This is less than when I was just assuming everything all at once. Then the rotational inertia of the arms, okay, for one, there's 2 of them, but a cylinder has an ml squared, ml squared per cube. Okay, it's 1/3 ml squared is for cylinder, treating the arms like they're skinny rods. Okay, so here we have 2/3 of this, 3.75 kilograms, and the length of these things is 0.9 squared. So that means the rotational inertia of the arms is 2.025 kilogram meter squared. Notice how much larger the rotational inertia is of things that are massively smaller. 3.75 kilograms each is a lot less than 50. I'm dealing with heading towards 8 kilograms in the arms versus 52 in the rest of the body. But look, the inertia, throwing those arms out, presents a lot more resistance to motion than having the arms in as part of the main cylinder. So when they're spinning super fast, their angular speed is super high with the arms in, and they throw the arms out, they immediately come to a noticeably slower speed, only by throwing out a little bit of mass. It's redistributing the inertia, and that changes the angular momentum because mass is a measure of inertia. Okay, and rotational mass has a different behavior than regular old mass, if you will, except in the most general sense of inertia itself. So at the end here, the total inertia, the total rotational inertia is going to be the body parts, your main trunk parts plus the arms, and you're going to get 2.34 kilogram meter squared when the arms are extended. But when the arms are pulled in, you only have 0.36 units of rotational inertia. A lot less, hence the speed is higher. Okay, because this conservation of angular momentum basically conservation. God, that's a really bad spelling. All right. Or scribbly, really bad writing. Conservation of angular momentum. That implies that my final angular momentum equals my initial angular momentum, which means my final I omega, rotational mass, rotational speed, equals my initial. Okay, so if any of those things change, then the speeds necessarily change. All right, so on one side we'll have a different rotational inertia. This is really just going to be, I'll call it IB and IC, if you will, because they're different and therefore I'll have different speeds. But they have to, the momentum has to go somewhere. So if the mass increases, the speed decreases. That sort of, if the inertia increases, then the speed has to decrease. So that's the thing here. It's not as explicit or necessary to pay attention to in linear stuff, but here it's quite noticeable. And number 10, last page. Soccer player extends her lower leg in a kicking motion, exerting a force with the muscle above the knee in her front leg. She produces an angular acceleration of 30 rads per second. All right. Obviously, this is a human being with a knee joint, and it takes force to produce this rotational motion of the lower part of the leg. Torque needs to be coming to your mind when you know that there's rotational motion involved with a force. I must be dealing with torque. So one of the things you could just blurt out on your pen, you could always just say torque equals I alpha equals RF. You know it's going to be that. Very likely that one or both of these things is exactly what you need. Okay. So I'm given the angular acceleration. I'm given the moment of inertia. Realize moment of inertia is the, I guess, the conventional by the book word for rotational inertia. Moment of inertia, rotational inertia, same thing. All right. And we know the radius. So really, what force is exerted? Force would just be I alpha over R. Really simple. So we take the 0.75 kilogram meter squared times the 30 rads per second square over the radius of 0.019 meters because it was given in centimeters. So force here is 1.18 times 10 to the third newtons. So, 1100, 1200 newtons, somewhere in there. So relatively easy problem, number 10 here. Need more space for number 11, so new screen. So 11, suppose you exert a force of 180 newtons tangent to some radius, another grindstone problem, solid disk, which means it has its own peculiar moment of inertia. What's the torque exerted? All right, part A. Torque, radius, and force. I know it's going to be that version of torque because I was given that. I know that torque is radius force. I was given radius force things. So this is an easy kill. 0.28 meters for that radius, 180 Newton force, 50.4 Newton meters. But it's not a joule. That's the thing. When you do torque, you get Newton meters. When you do force times distance, you get joules. Okay, keep that straight. Part B. What is the angular acceleration assuming negligible opposing friction? Obviously, this is telling me to sum all the torques because that equals, according to Newton's second law, I alpha. Somehow, the lingo of what is the angular acceleration assuming negligible opposing friction? Well, I want to know angular acceleration, and I know that torque equals I alpha. I know it's a solid disk, so that means I can look up what I is, which is 1/2 mr squared. I already know what the torque value is, so I can just go straight to Newton's second law, which sooner or later has to apply in any of these torque problems. And you get net torque. We only had one torque anyways, over this moment of inertia. So net torque over 1/2 mr squared. That's what it would be for a solid disk. So alpha is going to be 50.4 over half of 75 kilograms and a 0.28 meters squared. So my alpha, 17.1 rads per second squared. C. What is the angular acceleration if there is an opposing frictional force of 20 newtons exerted on the 1.5 centimeters radius from the axis? Here I do have to still get to sum of forces, and so I have to, this is one of the conditions of equilibrium, but it's the same thing we did before with forces. Sum of forces equals ma, but now it's sum of torques equals I alpha, all right? So the sum of all the torques will be the torque that we just dealt with, that we just solved for in part A, minus the torque due to friction. Okay? What we could do is we could just write that as torque sub lowercase f if you realize that f is for friction. So realize that in our case f is going to be mu n. Okay? So now I have 50.4, that was from part A, minus mu n, and it's going to be the friction force. Let me rewrite this just to be explicit. It's going to be friction times the radius that this force is exerted at. That's our torque. Remember, torque is always an RF sort of thing. And so that means I'm going to have 50.4 minus mu n r. So my sum of torques, 50.4 minus, oh, what is it? Just lost track of where I was at on my notes. 0.015 is the radius, and the coefficient. Oh, we were given friction, weren't we? Yeah, it's 20 newtons of friction, sorry. So I don't even need to bother with this mu and r. So 20 newtons, and the 0.28 meters that it works at, and I get to, basically that's just 0.3-ish. Wait a minute, it's not 0.28, it's 15 centimeters. I'm reading the other part of the problem. So 15 centimeters is what, 0.015? Or 0.15 rather. Well, I'm sorry, this is 1.5 centimeters. Let's be careful. Man, must be after lunch. So it's a really small thing like 0.3, so we end up getting our sum of torques, or the net torque in this situation, is 50.1 Newton meters. But that's not the end of the game, because it wants to know what is the angular acceleration, right? So this is where we just go to, well, angular acceleration is just going to be the sum of those torques over the moment of inertia. So 50.1 Newton meters over half the 75 kilograms and the 0.28 meters squared. And we get 17 rads per second squared. So we go from 17.1 radians per second squared to 17 radians per second squared by having a really small amount of friction come into play. So the angular acceleration in this situation, remarkably small, but so was the frictional force involved. That would be the point of doing this math. Really small friction, really small deceleration. Correct. One more problem. We get to stick a fork in it, call it done. Nobody wants to eat it, but here we go. Number 12. 12 kilogram motorcycle wheel. Oh, I forgot to include the figure. All right, it's a motorcycle wheel. Assume it to be approximately annular ring with an inner radius. So there's a formula that I'll soon show for the moment of inertia of an angular ring. And it's an interesting formula that seems to be, it involves two radiuses, the inner and outer radius. Okay, so we'll get to that as soon as we can. Motorcycle's on its center stand so that the wheel can spin freely. If the drivetrain gives us a big force at some small radius, what's the angular acceleration? All right. So part A, once again, we know that there's torque because it's a roundy thing and a force involved at a radius. So I'm going to have a radius and a force. Well, lucky me, I know that it's 0.05 meters, 5 centimeters, and a 2200 Newton force exerted at that radius, which means I have 110 Newton meter torque. Anybody used a torque wrench before? You know, they'll be in Newton meters or pound feet, something like pound inches, whatever is appropriate for that thing. And you're looking at that little gauge because you know you got to torque it to some certain amount. Otherwise, everybody dies. Okay. Oh, we're not done with this problem. So let me back up here. So I have that, and part A wanted us to angular acceleration of the wheel. Well, torque also equals I alpha, which means alpha is going to be the torque we just found over the rotational inertia, and the rotational inertia or moment of inertia that we need to do for an annular ring is going to be 1/2 of the total mass times the sum of the squares of the inner and outer radii. All right. So alpha will equal this 110 Newton meters that we computed earlier. 1/2 the total mass, which was 12 kilograms. And I have a 0.28 meters squared plus a 0.33 meters squared. Crunch away at all of that, and you get 97.9 radians per second squared. So part B, what's the tangential acceleration of a point on the outer edge of the tire? Well, we know that acceleration, tangential acceleration, we already used this a couple times, alpha r. It needs to be alpha r2, or the bigger radius. That would be the one that's the outer one. All right. So simple calculation, 97.9 times a 0.33, and you're going to get 32.3 meters per second, speed of a point out there on the edge of the wheel, or acceleration rather. So this can be meters per second squared. Part C. How long, starting from rest, does it take to reach an angular velocity of 80 rads per second? So change in angular speed equals alpha delta t. So my delta t, change in that speed over the acceleration. Change in speed was 80. Acceleration is 97.9. Takes less than a second. 0.82 seconds roughly. That is the end of that problem set.